All right. We are now doing dimension analysis. Okay. So inside there, we'll look at things like limitations, definitions, applications, laws of homogeneity of dimension analysis, density dimension analysis, mass dimension analysis, time dimension analysis, area dimension analysis, speed dimension analysis, volume dimension analysis. All right. So that those are the things we'll tackle and we'll be able to cover everything. And the rest will be just solving questions, which will be the tutorial sheet. I'll bring the tutorial sheet in the next lesson. So hope you are getting me. Everyone is getting me in this meeting. Okay, so again, if there are those who want to register, you can write the number is there 0964 122 411. Okay, 122 411. So that is it for those who want it. So you can tell others. Hope everyone is getting me now. We can proceed. So definition of dimension analysis. Okay. So I didn't want just to be saying, I want you to be seeing it. That's why I've decided to write it like that. I decided to type a document than just presenting a screen. So when we say dimension analysis, all right, this is the analysis of the relationships, all right, between fundamental physical quantities, which are, all right, so don't struggle about purely mechanical in nature, but you can say which are mass, length, and time. Or you can say again, dimension analysis is the relationships or is the study of relationships between fundamental physical quantities. I'll show you these fundamental physical quantities that I'm talking about, which are purely mechanical in nature. So if you want, you include this just to spice your definition. Sometimes you can just say which are mass, time, length, with the dimensions respectively as for mass you write m, all right. For length you write L, for time you write capital T like that. So these are the dimension analysis of mass and length L, time T like that. So these are purely mechanical. Every physical quantity that you know will be coming from these three guys. And I'll demonstrate what I'm trying to say. All right. So these quantities are represented by the letters. So these are the dimensions for mass, dimensions for length, dimensions for time. All right. So when I say what is the dimension for this, just look at that. Okay. Respectively, like I've been saying. So the letters specify only the nature of the unit C. All right. So it's only the unit. So we'll be relating everything to their units. All the physical quantities, now their units. Okay. For example, I tell you to say seconds. Second is time, right? The dimension will be T. All right. I tell you to say distance. Distance is some kind of length. So you put there. All right. Like that. The meters thing, okay, is about distance or the length. It measures the length. All right. So hour, whatever, if we have hours, seconds, stuff like that, we relate to T, okay? I mean, distance, we relate to that. Also, volume, we relate to L like that. Whether it's cubed, it will be L cubed. Whether it's area, which will be length, we'll still put length like that. So these are the units that we'll be looking at, not the magnitude, no. So the concept of dimension analysis, dimensionality is important in understanding physical quantity. In solving physics problems, we'll be using these quantities. All right. So let me show you something, how this dimension analysis will be coming about. All right. Okay, I've seen what I've typed. So we are going to have different dimensions. All right. So we are going to have different dimensions based on just what we want. So dimensions will be a lot. So it depends with what we are going to actually ask. So the thing is, master the units and you'll be able to classify where the dimensions actually comes from. All right. So I'll bring a lot on board and you should be able to specify, classify the dimension analysis. So dimension analysis, when I ask you to say, give the dimension analysis of this relationship, you express in terms of L, M, and T. All right. For example, um, I tell you to say, what would be the dimensions of, let's say, force? We know force is what? Mass times acceleration, right? Okay, is that okay? Then you look at mass is measured in kg, right? Then acceleration is measured in what? Meters per second squared. All right. So what you do is the dimensions for mass is always capital letter M. All right. We normally use this dot if you want. Then the dimensions for M relating to meters, stuff like that, that will be just a length. All right. Then the dimensions for second time, stuff like that, that will be what? T like that, squared. So the dimensions for force now will be M, L, then T, it to go there on top, and that will be what? A negative like that. You have seen? So that will be the dimensions for L like that. What if I tell you to say, give me the dimensions for area? Area is always measured. We are looking at units like I said, remember, squared, all right? So this will be this meter, this is meter, right? So it will be just L squared. So this is the dimensions for area. If I tell you to say dimensions just for distance, which will be measured in meters, okay, the dimension is the capital letter A like that. The dimensions for volume, volume will be measured in whether it's breadth, height, and the length. All right. Still, they still give the length dimensions. So this B is also L. Again, the H is also talking about the length. Even the length itself is talking about the length. So the dimensions for volume, it will be L to the power 3. Okay. The dimensions for power, not really that. What else can I talk about? The dimensions for velocity, which is measured in meters per second. All right. This means that the meter stuff falls under what? L. Then the second falls under T. All right. What else can you talk about? We have a lot. Okay, so that is it. What other dimensions can I talk about? Let's say density. All right. Density we know is measured in mass over volume. All right. This volume should be in cubed. The mass should be just in kg. So we'll say the dimensions for mass is what? Kg, not kg, but capital letter M. All right. So it's capital letter M. Then the dimensions for this mass over volume right there. Volume is always measured in meter cubed, centimeter cubed. All those, they are just dimensions, all right, under L. So we'll say L cubed. So the dimensions for density to be what? M, then L, it will be now to the power 3 like that. Okay. So that is it. So that is it about dimensions, all right? So if I'm to tell you to say what would be the dimensions of um acceleration, I've already given input acceleration. Acceleration which is measured in meters per second squared. This the dimensions for meters is falls under L. Meters, centimeters, distance, they falls under L. Then the dimensions for time, it will be times second squared. All right. Then we have L t to the power -2 like that. So that will be the dimensions for acceleration. What else can I talk about? There are a lot of dimensions. So long as you know that mass falls under everything, all the physical quantities that we looked at, they will be falling under this. Okay. So hope that makes clear. Then I want to introduce something to you to say exponential rules will be used under dimension analysis. So if I have L over L, let's say squared, this will just be 1 over L, okay? Because the L there will cancel like that. You can only multiply of the same dimensions, all right? Again, if I have L from different units, they are combined like that, this will be L to the power 2. You combine like that. So you use exponential or rules of exponents. All right, so be used the. So that is it about dimension. So we can draw a lot of dimension analysis, provided we know that this is falling under length, this is falling under mass, this is falling under density. Every physical quantity will be falling under that. Okay, what else can I say? Is there any example that I can give? Okay, let's say, what are the physical quantity that I can give? Or the length stuff, the density stuff, we have talked about those things. The volume, we have talked about it. The meters, the square, we have talked about all those. All right. It's just to know the units of those physical quantities that they'll be asking you. All right. Then we'll be able to drive the dimension. So that's how we can derive the dimension analysis of each kind, each physical quantity. So there's what we call principle of homogeneity of dimension analysis. So this principle states that we can only multiply, divide physical quantity with the same or different dimension analysis, all right, dimensional formulae at our own convenience. However, no such rules applies to what addition and subtraction. So this means that we can only multiply dimensions of same or different dimension formulas at our own convenience, but no such laws apply to addition and subtraction. What I'm trying to say is we can only divide, multiply. So, for example, so we can only multiply. So I can only multiply dimensions of the same quantity like this. I can have, let's say, t and what again l. All right. So this will be t l squared. I've multiplied this, okay? Or you can say l squared t like that. I've multiplied. You have seen they had different, let's say, different dimensions. You have seen, or same, or same. I've multiplied this l and l, and I've gotten a squared. All right, but we can't add l plus, okay, l. We can't add this. We can't say 2l. No, we don't apply. This rule doesn't exist. We can't we can't multiply, but each independent must be equal. So in a case of relationship or an equation like this, the dimensions or the terms on both sides equation must be the same. So this means that this is equal to that, and also this is equal to that. So that is the equation must be, that is if the equation must be dimensional homogeneous or homogeneity. So that is it, homogeneity. So homogeneity is about to relating to what actually, let me show you homogeneity thing. All right. So for example, use dimension analysis to check if the equation is correct or if the equation is homogeneous, all right, is same. So let me actually demonstrate that. So what we are going to do is we need to know that the dimensions, all right, I'll start with that. Like I said, we need to check if this is equal to that and also that is equal to that. So that's the goal we have there. All right. So we know that the dimensions for this is velocity, right? From the, this is the first equation under equations of motions, Newton equations of motions. Many of you who did grade 10, 12 can relate this. Okay, the dimensions for this is velocity, final velocity, this is initial acceleration and time. So the dimensions for velocity are what? I mean, the units, we are relating to units is meters per second, all right? I like writing down like that. The dimensions for this is also another velocity, but initial. So again, it is the SI unit for the same initial velocity or just velocity is meters per second. I'm writing per second or be like that. I like writing like that. Plus the dimensions for acceleration is what? Is meters per second squared. You have seen? Then times the dimensions for time is what? Just S. I mean the SI unit. These are SI units. Now I'll put the dimensions. The dimensions for meters is the length. All right. You see how sweet it is? Okay. So the dimensions for meters should be L. The dimensions for seconds, time, hours should be capital letter T. All right. The dimensions for meters again, it's L. The dimensions for seconds should be T. All right. Plus the dimensions for meters, it's what? L. The dimensions for seconds, stuff like that is L. Now we have, I mean, it's T, but time is T, but we have T squared there because from acceleration formula. Then times we have the dimension for S again second, which was for time, it's S, it's T. You have seen that 1T will go there. So we'll remain with L over T is equal to, again, L over T, again, plus L over T. So this equation is dimensionally correct, homogeneous, okay? It's homogeneous because it's giving this is equal to that, this is equal to that. In fact, we'll be using this concept to relate to what we want to find to, I mean, to the left, from the light, we'll be using to relate that to find an equation, all right? Okay. So for example, I tell you to say again, okay, I'll discuss that under application. So that's how homogeneity works. So we can check whether the equation is dimensionally correct or not. So that equation is correct. The equations should actually give both sides the same. So applications, why can we use this dimension? What are the applications of dimension analysis? One, we'll be able to find the unit of a physical quantity in a given system, all right? For example, I'll tell you to say, find the units, all right, of force, all right? So we'll say, okay, force is measured in what? Let me just put acceleration, all right? So acceleration is equals to what? Okay, so let me do this. Acceleration is equals to what? Velocity over what? Time, right? So that is the acceleration. So to find the units, all right, of a physical quantity, so be able to find the units of this guy, all right, in a given system of units. So these are the given system of units. So we are saying now velocity is measured in what? In meters, okay, per second, all right. Then again, we have 1 over this t that we have there, all right. So that means that this is also second, right? This is second, the time there, all right. So that means that acceleration is equals to, this is what? L, right, for meters. Then we have s times this, which is L, which is t squared, all right. So we can find this is the unit. We can now take it to say this will be meters, all right, over, all right, time is what? Second squared, like that. So this means that acceleration is measured in meters per second squared. So we have found the units of a physical quantity in a given unit. So given these units, we are able to find this. So that is one use of dimension analysis. Hope that is clear. So that's how we can use dimension analysis. Okay. So that's how we can use dimension analysis. What else should we talk about? Okay, let's go to the next point. Hope you are listening there in the meeting. To find the dimensions of physical constant or coefficient. So suppose whenever each variation that will be meeting, each relationship, suppose I tell you to say the force of a particle depends on the force of the particle depends on the A and what? B. All right. So this means that whenever, okay, so let me write this. I want to show you how you be coming up with the equations or relationship. There are questions that, let's say, the force of a particle is found by actually shaking or disturbing its mass with a bit of involving acceleration in it. So I'll say the force of a particle is given as, all right, is given as y. So I'll say varies as y. Then with just a change in also x, all right. Find the dimension analysis, find the dimension of f, all right. So what we do is we always relate to this, all right. um in fact, I'm not supposed to draw it like this. Say the force of a particle depends on the mass, all right, and acceleration like that. Okay, so when you are coming up with an equation now, you always write a constant, right? Then you write your mass and acceleration. Constant always must be there whenever you are coming up with an equation. Remember those equations you are coming up with in grade 10 and the topic code in mathematics paper 1. You remember the topic, I won't mention it. So variations, by the way. So now if you are to calculate the constant, you'll be able to relate to say k now is equals to f, all right, then m a. Okay, so the dimensions will be obviously a constant, so we'll be able to find, let's say, the dimensions like that, but not really that this point is there though. So and also we'll be there to check the accuracy of a given equation or relationship, like I demonstrated on homogeneity. An equation or relationship is correct or accurate if the dimension though of each term either side of this equation are equal, like I said, if a plus b is equals to c. So you need to know that this is equal to c and also this is equal to that. Even this is equals to that. So they are equal. Okay, each independent term is equal. So we'll be also able to derive the correctness of an equation or relationship. So we'll be able to verify like that equation we made. So we'll be able to verify whether what is on the left side is equal to what is on the right side. And it is true. Try put the dimensions there and also to put it will be the same. So we'll be also able to convert physical quantities from one system to another. So we'll be changing, let's say, acceleration from density. So we'll say density is gotten by mass and the acceleration, I mean volume. So these are the physical quantities. So we'll be able to have this from this. These are what we call derived quantities. So we'll be able to convert a physical quantity from one system to another. So from just these two physical quantities, we'll be able to have density. So those are, so I want you to repeat. Dimension analysis will be used to actually find the units of a physical quantities. One, we'll be able to find the dimensions of a physical constant or coefficient. 2, we'll be able to check the accuracy of an equation, that is 3. We'll be able to derive the relationship of an equation, that is 4. We'll be also able to convert one physical quantity to another from given systems. So those are the 4 points that I need you to master, 5 of them. That is it. So this dimension analysis, yes, we have dimension analysis, but it has disadvantages as well. We'll see how when we'll be solving questions, okay? So it has limitations as well. It is limited to some extent. So what are these limitations? This dimension analysis, it does not depends on the magnitude. It only depends on what? Units. Okay, that is, it is limited to that. We need magnitude in as much as we derive these units so that we see what relate. Because a constant or a magnitude will be there actually to what? To give us the relationship, how it affects one or the other variables. Okay, so the numerical constant having no dimensions cannot be deduced by method of dimension. So that constant, okay, let's say force is equals to k mass times acceleration. So this k, okay, the numerical constant having no dimensions, this one, cannot be deduced by a method of dimension analysis. By the way, we can't even find this. Even on that point, in fact, it's invalid the point that I gave at first, where I said we can derive that, relate it properly. So we are saying now this won't be we won't be able to find the constant of this value, but it will be there to find the units of this value. So differentiate with that the point I've given on top there. So we'll be able to find the constant units, not the value, but we need the value so that we see the relationship, you see. So this method is applicable only if the relationship is of the product type or division type. So only if we are multiplying something or only if we are dividing something. That's when it is applicable. It fails in the case of exponential trigonometry functions. So it fails in short, it is limited to exponential and trig functions. This method is suitable if the physical quantity depends on more than 3 other. I mean, the method is not suitable or applicable to things that does not include L, M, and T. So exclusive to these 3, the method is not applicable. Okay, like let's say the moles and stuff like that, it won't be applicable to this. So quite often it is difficult to guess the parameter on which the physical quantity depends. So this is not that effective. But what I want you to master is, these are the points that I want you to master. It does not give the magnitude. I mean, it does not depends on the magnitude. These are the limitations. The other thing is, does not give the value of the constant. This dimension analysis is only applicable to product type. It does not relate to trig functions like sine, cos, stuff like that. We don't do that. The method is also not suitable for physical quantity that depends on more than these three guys we have there. Okay, it is difficult sometimes to guess the parameter of the physical quantities where it depends on. So those are the points that I want you to master. Know the limitations. It's only applicable to product type, not trig and exponential. Okay, it only depends on three physical or dimension type three, which are this and this and this. Okay, it also fails to give the value of a constant. Those are the points you need to give under limitations. I've preached about this, so make sure you understand them. So this marks the end, the load. So watch out for a tutorial sheets. We'll drop the tutorial sheets. Subscribe to our YouTube channel. Thank you very much. So otherwise, this is what I had for dimension analysis. Everything has been explained: the application, the limitations, the density dimension analysis, homogeneity principle, the volume dimension, the speed, the mass dimension analysis, the time dimension analysis. We have explained all those. Thank you very much. Um, Keep watching. And you can register there. The line is there if you want these lessons. Otherwise, the documents are also there. Solve the documents. Thank you.